So now that the main thing to realize is you have, you can multiply stuff by constants, negative, whatever. You can also operate on stuff with differential operators. To try to make the coefficients, we're going to look at this as a coefficient now, even though it's made of an operator and a constant pairs. Make the coefficients of one of the variables the same. Just the same idea as systems of regular equations, but we just have the operator as another level of something we can use, that we have to use. So, what would you rather eliminate? The x's or the y's? Yeah, so maybe the x? Sure, okay. So then, to do that, I have to do something to both equations, of course, right? I can't make this become this. So if I take the first one, what am I going to do to it? Yeah, operate by t plus 1 on it. So there's that t plus 1 operating on the first guy. So this is operating on plus 1, and then I can take the second one, and I've got to be just a little careful. What can I do to the second one? Yeah, operate with a negative differential operator. Just so they end up being opposite signs. So these parentheses are not necessary. I have no idea why I put them there. So if we operate on this with negative, I get negative d plus 1 dx minus d times d minus 1y equals negative d operating on 4e3t. I like it. Now you didn't have to do what I just did. You could have tried to eliminate the y's instead. You would have used the same idea we're using right now. So now if I add these two together, all the x stuff goes away. Right? Let me see if you guys can do the next step. Because you love when teachers do that. Let me do all this easy shit. No, you guys do the hard next time. And while you're doing this, you just, how am I going to handle this? Yeah, you could start distributing, but I can keep the y at the end of everything, right? So then I get d cubed plus d squared minus d squared minus negative, so plus 1. Plus 1d, that's my bad. Plus d. D, there. Now on this side, what is this? What is d operating on that? What does d represent? Yeah, d by dt. And really that explains a lot. That explains why this by itself doesn't mean anything. It explains why things have to come after it. Right? If I wrote y d by dt, that doesn't make any damn sense. So I got to put the y after so that it goes into it. That's the only thing about operators is they have to operate on something. So d e to the 3t would be 3 e to the 3t plus e to the 3t is 4 e to the 3t. And what's negative d operating on this? Well, the derivative of this would be, yeah, so it would be negative 12 e to the 3t. All right, let me stop there. You guys seeing what's happening? This is not the only way to do this. You could have killed the y's, or just kill the x's. Just kill somebody. And now I get this, and what does that start to look like? Oh yeah, so you guys who are working on this, you shouldn't end up with the cube. I'm not sure exactly what happened. What do I do from here? I don't know if you guys can start to see this, but I mean, again, if you need to right now, what is d cubed y? So I got d cubed y plus dy equals negative 8 e to the 3t. So what is this written out? Yeah, d cubed y dt cubed plus dy dt equals that, or even y triple prime plus y prime, which, yeah. So really, I don't need all this shit. I just got m cubed plus m. So I can look at the aux. I can start to solve this. I have a differential equation with one functional unknown. I can attack it. We killed the x's. Now I can step back and think about earlier chapters. What chapter am I in? What method am I going to try to use? You guys with me? This is constant coefficients. Beautiful. Aux. So I get m cubed plus m equals 0. I'm looking at the associated homogeneous. All right, to get the yc, and then I can worry about the yp. So this is m squared plus 1. So it's just m is 0, or m is
Plus or minus I.
plus or minus I. So I get for yc, I get
C1.
yep, e to the 0. Yes.
How did you get when you added d plus 1 times e to 3t? And then,
So what is this? So this is, the derivative of this is just 3e to the 3t.
oh, okay.
Plus e to the 3t, that's 4. So that came from here, and this came from here.
Okay, gotcha.
Yeah, I just kind of did it and then wrote them down, so I didn't have to write them over and over. So this will be c1 plus c2 cosine t plus c3 sine t. I like it. And now I have to figure out y p. I like it. Cause. So this is where, is this anything to worry about? No, thank God. Right? It's not that kind of problem. I can assume an answer in the form of a e to the 3t, y prime is 3a e to the 3t, y double prime is 9a e to the 3t. Are you guys with me? Is that easy? And then I get, so dq, and then y triple prime, because I got a d cubed up here. Y triple prime will be 27. So we get 27. Let me do this in different color. 27. Ooh, you're staying on my top of my list. A e to the 3t plus dy 3ae to the 3t equals negative 8e to the 3t. So you get 30a equals negative 8. So I get a is negative 8 over 30, which is negative 4 over 15. Is that cool? So far, so now we got y of t, right? What do we have? So now we know y is c1 plus c2 cosine t plus c3 sine t minus 4/15 e to the 3t. So that's y. And now you could either do everything we just did for x, or you could try to use this to figure out x. Right? We could plug that back in. To either one, I think I'd rather use this one. You could do two derivatives of this easy enough. It doesn't really matter which one you do, to be honest. Is that decent? And then you're going to have to integrate once to get x, and that does introduce that constant we talked about last time. Okay, maybe. Is that decent? Is that all right? Okay, so I need you to realize it's not just weird-ass Jeff bringing up old algebra stuff and making your life miserable. It is just a fact. There are so many places in math where factoring things actually happen because it just naturally occurs. So a lot of times when you first learn factoring, you're like, well, you got to be, if you made that 8 and 9, it would never factor. You got to do quadratic. So why would you learn any factoring methods? Because there are millions of places in nature that lead to these equations where that happens. So knowing how to factor is important, or at least know synthetic division and know how to figure out what to try with synthetic division. Something. This wasn't that bad, but if it was d cubed plus 1, it should not be the end of the world. Or if it was 4 terms, it should not be the end of the world. Yeah. All right. I just kind of... Is that all right if we stop there? Is that all right? You guys are cool with that? I mean, now you just plug this in. You take a couple derivatives, so dy, d squared y. Now you know what that is. You plug it in, you subtract that stuff, and then you integrate once. So you get what x is. Okay. Anything else from homework stuff? We've only done that one section. Anything else from 4.9? Okay, so if you weren't here last time, I made 5.1 extra credit. And we got into 6.1. Anybody need the handout from 6.1? Okay, all right, so let's do this thing. I think last time I didn't really get anything specific, but I want to get to the point where you do the ones at the bottom of this, So let's just recall, the main thing we use is ratio test for us, to be honest. I don't know if you guys remember how many tests there were, comparison tests and root tests and ratio test and patience test. Yeah, they're all patience tests, right? That's true. Okay. So look at look at this. So the general form for power series centered at A is this here. Did I start at 0? So it's a pair series centered at A, meaning the infinite polynomial you get matches exactly with the function it represents at A. The minute you get away from A a little bit, you have to go out further in the polynomial if you need to be more and more precise. I don't know if this sounds familiar. If you guys remember this stuff. So there's this is a function of n. It's some constant, really, compared to x being the true variable for the polynomial. N, though, is a variable for the summation, but for any value of n, this is a constant. That's why I call it c, but it's dependent on n. So for this one, look at the first problem here. Where sorry. First question is, what's Cn in this problem? What's Cn?
1.
Yes, 1 over. I like it. 1 over n factorial. I love it. Real quick thing about factorial. How many of you guys have forgotten about factorial? All right, when you looked at this, you thought this was just x to the n over n. All right. Real quick, remind me, what is n factorial?
N times n.
Until you get to 1. So, and to be honest, you can define factorials for things beyond integers. It just gets a little weird. We're not going to do that right now. Don't worry. So, for example, if I had n plus 2 factorial divided by n minus 1 factorial, can I do anything with that? Yes, and I like to call it shucking off parts, right? Start to write out what n plus 2 means. N plus 2 factorial is n plus 2 times n plus 1 times n minus 1 forever. So you just put the factorial there to mean forever, or, as long as n is still big enough, because we know what n is. All over n minus 1 factorials, and then these cancel. Right? I mean, that's the basics of how you handle factorials in series. Especially when you do ratio tests, you're gonna get stuff like that. So, if I try to apply the ratio test here, what's the basic idea? So if I look at this as an, the ratio test says take the limit as n goes to infinity of the absolute value of the ratio of the next term to the previous term. And I try to get you guys, if you remember your geometric stuff, the geometric stuff kicked so much ass if you let it. As long as the multiplier was less than 1, it would converge. So this guy, this is beautiful. This is basically looking at the multiplier. And it doesn't have to be a constant multiplier. It just says this element, how did I get to it from this element? What did I multiply to get to it? As long as that multiplier eventually becomes less than 1, that's just like saying r is less than 1 for geometric. It's beautiful. Right? It's not a separate thing. It's actually the same thing. So let's set this up. Try to set that up. What does that look like for this? Write it down. Set that up for this. All right, so let me see if everybody's got that set up correctly. This should look like the limit as n goes to infinity. What would a sub n plus 1 be? And basically, the way you do the division is you multiply by the reciprocal of the original, so you just take this and plop it down there, right? So you get n factorial over x to the n. And then what happens is, now you can see this thing that just basically happened to us up there. This thing goes to infinity. What happens to the x stuff? Yeah, it's just an x left. I'll just put it over there. See it over there. And what happens to the n stuff? Which one do I want to shuck off? It always sounds like it's almost shuck it off. I mean, the bottom, we always take the big one, of course, because it's got extra shit, right? So it makes sense. So what do I shuck off of this dude? It just sounds weird. That's why I like saying it. N plus 1. And then I have n factorial. That shit goes away. That's nice. It's nice to cancel an infinite number of things, possibly. N's going to infinity, so So what is the limit as n goes to infinity of x over n plus 1? Yes, because it doesn't matter what you make x. Make x the biggest number you can think of to itself as a power. To itself as a power. I mean, it doesn't matter how big you make it. That is eventually going to overwhelm it. So this is going to be 0. When is that less than 1? When is that less than 1? Always. So what values work? All values. So what's the interval of convergence would be negative infinity to infinity. So if this would have been like, if that would have been absolute value of x left over, then it would have been absolute value of x must be less than 1. That would have been, then it would have been negative 1 to 1. We would have actually had to check the endpoints then to see if they work or don't. Does this sound vaguely familiar? All right, you guys try number 2 there. Oh, that's right. That's the one I forgot to change.
Oh, right there. Are we getting this?
What problem?
Is it
What's up?
that one there? Is that what we're doing? Which one? Which
No, I'm
number
sorry. At the
two?
very bottom.
Oh, okay.
Yeah, I'm sorry. These are all already done examples. We just did number 1, right? X to the n over n factorial. So now
Yeah.
number 2 at the very bottom.
Okay, thanks.
Cool. It's fine, Ethan. Don't. I'm not like, do it if you can find it. You just let me know if you don't know. Oh,
That was a
anyone?
trick question for a second.
Left mine at home.
2?
Anybody else? Everybody else? Sorry. Oh, cool. Oh, no. That's going to be a neat part of that. So you should watch the video, and it looks like we had an earthquake. All right. Oh shit, that's right. Just gave me my last one away. So 2. By the way, before I forget, it's kind of bugging me. Make that last one a equals 1 to infinity, and you should probably be able to see why. And number 4, put a 1 there instead of 0. I knew there was something I forgot to change.
0.
Yeah, it's always nice to start with infinity. What was the square root of n?
Times n.
X to the n? Okay. So then, what's it look like for the ratio test?
Square root of n plus 1 times x to the n plus 1 over square root of n times x.
Like it? So this limit here what's the limit of these radicals? You can take the limit inside the radical. So you really just have the square root of the limit as n goes to infinity of n plus 1 over n. And that is pre-calculus stuff, right? Remember that? It's basically horizontal asymptote shit. Remember that stuff? Same powers, ratio coefficients, 1. I like it. So this is just 1. And of course this just reduces to x. And so that limit has to be less than 1. So that basically defines the interior of the interval. Now we've got to check the endpoints. So how do I rewrite this as an interval? Negative 1 to 1, yeah. It's funny when I see absolute value inequalities. This is a haunted house. Stay close to me. So here I am. Don't get further than 1 away from me. Greater than is a restraining order. Stay the hell away from me. Right? Sometimes I teach that and somebody's like, I have an active restraining order. I don't want to hear about this shit. So how do I check the endpoints? Yeah, so if we check n equal to negative 1, got it, and x equal to negative 1, it becomes this. Remembers what that's related to, and when you have a negative 1 to the n, alternating series. In order for an alternating series to converge, you need the limit of this part to go to 0. Obviously, the limit as n goes to infinity of square root of n is not 0, it's infinity. So you can see it's even worse when I plug just a 1 in. It ain't got no chance. So this, no good. So I can't include negative 1 in my interval. So I'm going to keep that as strictly less than. And if I check 1, it's even worse. It's just, I'm going to add up all the square roots forever. Well, that's never going to get to a finite number. It's just going to go crazy. So I can't include 1. So this actually ends up being the right thing. But you got to check the endpoints because maybe sometimes both or one of them actually leads it to being convergent. All right. Some of you guys are like, I can't believe I'm doing this again. thought I escaped that damn class. No, there's a reason that that's in there is because it's applicable in a lot of places. Yes?
Sorry, so we're plugging that in to check what?
Yeah, all the x's between these work according to the ratio test. The ratio test breaks down if it equals 1. So I have to check the endpoints to see what it does here, because it might converge or it might diverge. We checked it, it diverges at both. But if it like converged at -1, if it would have been 1 over the square root of n, that the limit is n goes to infinity, that would have been 0, then I would have included -1. That would have been a little more interesting problem, because then I would have had to do a p-test for the other one. And again, not the, you want to get a job p-test, but. Are you guys, how are we doing? And again, this is, I'm trying to dredge up some memories and trying to make you realize you got to review this. That's why I gave you that. And I'm trying to make it very targeted to what we're going to be mostly doing. What's the third one? What's the third one say?
Negative 1 to the n times x to the n over 3 to the n times n plus 1.
Like that? Okay. Oh, I like it. Yeah. All right, so let's see. So the limit, n goes to infinity. Now, you realize this is an absolute value, right? So if there's any -1 influence in there, just forget about it. That shit goes away. So I end up with x to the n plus 1 over 3 to the n plus 1, n plus 2 times the reciprocal of the original. Yeah. So what almost always happens? Well, what always happens to the x is it just becomes x. Let me put that shit over there. What happens to the 3's? Where do I have one left? Where? Bottom. That's where there's more of them. And what's the limit of this here? 1. So I get limit as n goes to infinity of x over 3 is of course x over 3. It's pretty cool that, because of course there's no n dependence. There's no n dependence, so it doesn't give a shit what n does. It's going to be itself. And that has to be what for this to converge? That has to be less than 1. So the absolute value of x has to be less than 3. So -3 less than x less than 3. Okay. And now, of course, I have to check the endpoints to see what they do. I like it. So if I check -3, I'm kind of doing this with you because I have another little handout where you're going to be doing some of this yourselves. So if I check x equal -3, gather, I get some -1 to the n, 3 to the n over -3, yeah? -3 to the n. 3 to the n, n plus 1. This is kind of nifty. You guys see how all that kind of shakes out?
Because -1 would it be harmonic?
Harmonic is 1 over n. That's the harmonic series. You're thinking about alternating.
Alternating, yeah,
But does that piece survive? What happens here? Break this out. So that's -1 to the n, -1 to the n, 3 to the n, over 3 to the n, n plus 1. These kill each other. Yeah, it just becomes positive 1. Always. And then these kill each other. So I end up with 1 over n plus 1. And we basically just gave this away a second ago. Does that converge or diverge? Diverge. Because like it's the harmonic series, right? It's the basic one. P, for 1 over n to the p, what's got to be true about p for it to converge?
It converges. The but not fast enough.
P greater than 1. There's a difference between saying the sequence converges versus if the series converges. The sequence converges to 0. Not fast enough for the series to converge. I like it. So always students get the idea if the limit as n goes to 0 does not mean it converges. It means it might converge. If the limit of this is not 0, it definitely diverges. It doesn't even have a chance. Okay. So this guy diverges. Now can you see what's going to happen when I put a positive 3 in? What's not going to cancel that canceled here? If I put x equal to positive 3, and you guys see everything's going to happen the same way except this wouldn't be here, right? If that's not there, then that's still here. Now I can apply, the alternating series test, because it is alternating, and all it says is the other piece has just got to go to 0, and it does. Because this is nice. This guy doesn't get out of his own way. This guy kind of like kills itself as it goes. Yay, oh, yay, oh. So then it definitely converges. As long as that's going to 0 and it's alternating, it's going to converge. So that means the actual interval is that. You have to include 3, because 3 leads to a convergent series. I'm hoping this sounds familiar. It's been like 8 years since you took 280. Sorry. You definitely want to review. All right. Let's look at that last one. And then I'm going to unleash you. Well, and then we still have to talk about a few other things. What's that last one? I asked you to change it to 1 to infinity, so it actually becomes a valid question. What's the inside?
X minus 5 to the n over n squared.
So this is a power series centered at
Maybe a little
5. Yes.
No.
All the other ones we've done has been centered at 0. This is offset by 5, so centered at 5. Right. And just very quickly, this would be x minus 5 to the n plus 1 over n plus 1 squared times n squared over x minus 5 to the n. So as always happens, I'm left with a single x piece. And then what's the limit of these two? What's the limit of this ratio? 1. And so this has got to be less than 1. And now, of course, here's where you have to really write it out and solve it. It's been shifted. So negative 1 less than x minus 5 less than 1. So then 4 less than x less than 6. Just add 5 to all sides. Now you guys try to check 4 and 6. See if it converges or diverges at those. I'll take that for that. So, I mean, when you plug a 4 in, you get negative 1 to the n, alternating. 1 over n squared goes to 0, so that's convergent, right? When you plug a 6 in, you get 1 to the n, which is 1 over n squared. 1 over n squared is a convergent p series, like p thing, yeah.
Yes,
so
P
that's,
series.
yeah. So that's going to converge also. So the interval is 4 to 6. What's the radius? 4 to 6. How far away do those get from the center? 1. I mean, the radius, the idea of a radius doesn't change. It's how far the ends get away from the middle. That's all. So if it talks about the radius of convergence, you just see how far is that away from the middle. I mean, it's going to be, and actually you can see it right here. That's going to be the radius. In this case, yeah. All right. All right, so that's kind of like the stuff you did in 280. Very brief, quick overview. And I'm going to bring it into 285 a little bit. We're going to say, how do I check a series solution? Because you know that's one of the first things we're going to do. As we've seen in all these chapters, what's the very first thing we do? Check the answer. Because we're not going to tell you how to get the answer yet. We just want you to be able to check the answer. Like, all right, here we go again. So here we go. We have a really weird looking answer, some infinite series answer. We have to be able to check it to make sure it works, which means I have to know how to take derivatives of an infinite series. And please, dear God, it is not difficult, because all infinite series are, power series are polynomials. Yes?
Does the alternating part change if the p series still converges? Because wouldn't it alternate for 4?
Totally, yeah. Yeah, in fact, that's the way I talked about it. Didn't even think about the p part, but it's alternating with a limit of 0, so that's
The only
convergent
time it gets weird
automatically.
is when you have trig functions, they can actually do some weird stuff.
So you could say this series converges. Who remembers the name? The series converges.
Yeah.
Series converges.
Absolutely.
Absolutely, yeah. Because if I take the absolute value of it, it still converges. So that's why we call it convergent, absolutely convergent. The other type of convergence is conditional convergence. The sum of -1 to the n over n is conditionally convergent because it doesn't converge if you take the absolute value. It only converges if you leave the portdude alone, right? All right, I like it. Okay, so let's take a look at a series and how to take its derivative. And I'm not sure if I have to do this, but I'm going to just do this just in case I do. Can you write the first few terms of this?
Is this actually 6-1 now?
Still 6-1. Just the first few terms. Just write the first few terms. So what do you get? 1. That's a neat sound. Okay, what's that? Now, take the derivative of this side.
Squared.
And of course, the next one, let's do one more just because. Plus 4x cubed. Now here's the part that people really, really, really hate, which shouldn't be true because math is all about patterns. And this, how do I write the summations for this? Yeah, so this is like, if I say 1, 2, 3, if I start at 1, but if you think about it, this started at 0, didn't it? This starts at 1 because I lost something. Right, so it kind of makes sense in that way. So if I start at 1, then that's going to be n, because that's 1, 2, 3, 4, that's following n. X to the, yeah, because for 1, for the first one, it's 0, so it's got to be offset by 1. Now, do you see how this is really stupid? I just want to make sure you guys see why this works. This is like the power rule. That's how it's written. Can't I just apply a derivative directly to this damn thing? Wouldn't that be x, the n comes down, x to the n minus 1. The thing you got to realize is you do have to write 1. That's kind of like part of what happens with series. Because what happens if, well, you know, if you put a 0 there, why is it not that terrible? What if n is 0, you get 0. So really that's why it goes up to 1. There's no need to write n equals 0.
But it's not. It's the same thing inevitably.
Yeah, exactly. It's the same thing. Isn't that like, if you didn't know how to do this, you should be going, oh, thank God. It's just the stupid rule. All right. How are we doing so far? Okay, okay. Now. Maybe I should give this to you and let you do the first 4 before I get into the last idea. Because the last idea is kind of like the newest idea of messing around with series. YouTube string of mess around with series. So you guys try 1 ABC and number 2. You can look at number 3 if you want to, and if you kind of know how to do it, try to do number 3. I haven't talked about it yet, so.